So I just want to, at the outset, say that basically I have given this talk in a number of different contexts for different audiences, and I just want to apologize in advance if I'm emphasizing things that may, I wasn't sure how to pitch it to this group. So the remedy for that is to ask questions, and for the people in the video, that's their, they don't have that opportunity, so they'll have to email me or something. But basically, please, if I'm not covering what you're interested in hearing about, let me know. Just ask questions. Don't raise your hand. Shout out, because I won't see your hand. The project that I've been working on for the last several years at Smith-Kettlewell, the Smith-Kettlewell Eye Research Institute, is called TMAP, which stands for Tactile Maps Automated Production. And it's the concept is very simple. It puts together geographical information, such as vectorized map data, with embossing and tactile production technology and distribution over the internet. So if you've got a means of producing tactile images, such as a Braille embosser, and you've got access to the internet, and if there's a site such as mine, which is serving embosser-ready tactile files, then you can actually, for the first time, have well-formatted, standardized tactile street maps of any area that you might want, so long as we've got that area in our database. I'll talk a little bit later about what the data set is that we're using and what our limitations are, but basically right now we've got the whole US, and we're still in a very limited rollout. There's very few users, basically because it's an experiment, it's scientific research. We don't have the wherewithal to do a lot of technical support. So we're just studying how people use this technology and what sorts of advantages or features they might get or want from this. So the idea here is basically to provide high-quality tactile street maps to people, blind and visually impaired people, to facilitate their ability to get from place to place. So that's, there are a number of different terms for that. I'll use a few of them. Wayfinding is one. Orientation and mobility is a term that I'll also use a little later on. But basically, for blind people, it is a different proposition to get from one place to another than it is for a sighted person. You need much more detailed information ahead of time about what sorts of turns you might take and what sorts of landmarks you might encounter. And for that reason, tactile maps are a hugely helpful tool for blind people to get from place to place. The reason I wanted to come and give this talk at Google, I borrowed your logo there. My friend said that I might get in trouble for using your logo, but I'll delete it if that's a problem. But basically, the Google mission has some very interesting crossover with ours. And in fact, the words universal and access are featured prominently in the Google mission statement. So I think that one of the things that I'm thinking about, and I hope you will think about, is how Google might consider either working with us or in the future producing some sort of facility to produce tactile maps that would be extremely useful to a lot of different types of blind and visually impaired people and people who work with them. So who does need the tactile street maps? That's your customers and your clients are always one of the most important things you need to think about. Obviously, I've already talked about blind people need tactile maps. That's those are the end users, but there are also some ancillary users, such as orientation and mobility instructors. These are people whose job it is, whose profession it is, to train blind people on how to get from place to place. So they teach you how to use a cane or a dog. They teach you the landmarks that you might look for along a specific route. And in fact, they very frequently use tactile maps. But in these situations, until now, orientation mobility instructors have had to create their own maps by hand. It's a very arduous process. And then, of course, the other group of people that might want to use tactile maps are teachers of visually impaired kids, to teach young kids how to teach them to develop map skills and tactile exploration, which have a whole lot of crossover benefits in terms of being able to read diagrams related to mathematics and science. It's a synergistic proposition to be able to have these tactile maps and to educate kids in tactile maps early on. The idea of tactile maps basically facilitates a bunch of different types of learning. Being able to map a two-dimensional space on a piece of paper to a real-world space promotes a lot of different skills related to cognitive map development. In the classroom, of course, there are a bunch of, not in the classroom, but in orientation, mobility, independent travel, there are a bunch of advantages to tactile maps. You can learn about how streets connect with one another. You can learn about what the intersections look like, and that's going to facilitate the choices you make in very dangerous situations like street crossings. For example, if you know that there's an intersection with a bizarre or unusual shape, you have a much better chance of navigating your way across that intersection if you know what the shape actually is. Or, conversely, you can choose an intersection that isn't so funky. Then, of course, the educational aspects of tactile maps. My project focuses on street maps, but of course the technology is broadly applicable to a lot of different map types. So it would facilitate blind and visually impaired students who want to study issues like demography or natural resources, or politics, political science, that type of thing. Well, as you know, color doesn't, we would have to remap that particular parameter, but no, and besides, it's too depressing. So there's a chicken and egg problem here. I referred to it already. Basically, the problem is that production of quality tactile maps is very difficult. Therefore, there aren't the teaching materials available for teachers to teach blind kids how to read maps. Therefore, blind and visually impaired kids, when they grow up into adults, don't know how to use maps or have any experience with them. And that leads to the original problem, which is a basic lack of availability. No demand, no supply. It's a very simple problem, but it's a vicious one in our case because they would be extremely beneficial. So that's one of the things we're trying to address. So just to make it really explicit about why tactile maps are difficult to produce, it's not as simple as taking a print map and saying, okay, I'm going to make a feelable version of this print map. And many of the tactile maps that you'll see in the world, maybe in public places or otherwise, are exactly that. They're just feelable print maps. Feelable print maps make some of the most useless tactile maps around, and also serve as really bad advertising for tactile maps in the blind community because it makes people think, oh, that's not going to work for me. So here are the reasons why it doesn't work. Basically, there's Braille, as I was talking to Mark about this morning, Braille doesn't scale. It comes in one font size or maybe two, and takes up an enormous amount of space relative to print. So the standard Braille, an 8.5 by 11 page, might hold 100 Braille words. Okay, that makes labeling and annotation of tactile maps and diagrams really difficult. So you almost always have to abbreviate and then create a legend or key that's associated with the abbreviations. Braille doesn't come in a lot of different fonts or colors or shadings. Braille is essentially black and white, and most of the production methods Braille embossers that produce tactile diagrams are capable of producing a dot or not a dot. And that's analogous to black and white, so you don't have all of the color coding options that you have in print maps. So you need to be very, very careful about how you code your information on a tactile map that doesn't use color or rich texture. And finally, you don't have the opportunity in Braille or in the tactile modality of if there's a piece of the map that you want to see better, you can't take a closer look. There is no zooming in the world, in the tactile domain. What you feel is what you get. And that makes it a very difficult proposition to create a detailed tactile map. So we're fighting all of these, you're sort of, in creating a tactile map, you're trying to balance these various requirements, and there are more, but I'm not going to go into excruciating detail, but suffice it to say that creating a tactile map requires skills that are different from creating print maps, and not everybody has them, so that is part of what contributes to the limited availability. Production by hand of tactile maps, which is how it's been done until now, is a very slow and arduous process. It's more art than anything else. And basically what you have to do is you have to draw on the back of a piece of paper with something like a tracing wheel, which is like a gear. It makes dots on the reverse side. And then when you want to feel the map, you actually have to turn it over and feel the map, which makes it for doing any kind of corrections or additions or changes is a very, very slow and painful process, and has generally been done by volunteer transcribers and other magnanimous people who donated their time. But there have been very few professional map creators because the cost of the time is actually, if you really build for your time creating a tactile map, it would be prohibitive and nobody would be able to afford it. So another factor involved in the dearth of tactile maps. So there's another type of map that I want to talk about also, which has been, with the sort of increasing availability of computers and touchscreens coming around, and that's audio tactile maps. And basically, this technology involves a tactile overlay on a touch-sensitive surface. The tactile overlay is created by some sort of embossing or engraving tool, and then you place it on the touch-sensitive surface hooked to a computer. The computer somehow knows what the overlay is showing and has regions mapped to those map features. So when you touch a spot on the tactile overlay, the computer is able to provide auditory feedback in the form of either recorded sound or synthetic speech about the object that you're touching. And you can really richly layer information in this way, because basically, with this technology, the requirement for labeling is much reduced. So you can offload all of your labeling information into the auditory channel. And that gives you the ability to make much clearer, more concise maps without a lot of text clutter, which really impacts readability of the maps. The skills required for audio tactile maps is obviously you need to have some programming skills to create these, so it doesn't just come from, again, we run into a situation where you need skilled labor to make a map. And then you need some other form of skilled labor in the form of the production. You have all of the same problems with the original paper-only tactile maps, or you're doing collage, or you're doing engraving, which again requires special skills. So basically, there's a long way of saying ain't no tactile maps available unless you go to a method like we're doing, which is tactile maps, automated production, which basically with the automation involved in the algorithms that we're using, completely eliminates the need for a skilled map producer. And if you've got the the internet and a production method like a Braille embosser, which many people do, you actually can just download and print out or emboss out a high-quality tactile map of any street network in the US, which is completely as simple as it sounds here at Google, which you do maps all the time. It's a completely revolutionary technology for us, just by putting some simple off-the-shelf things together. So the TMAP, now I'm going to get, for those of you who've been sort of rolling your eyes waiting for the technical stuff, I'll start to talk a little bit about that stuff. The user interface model works like this. The first thing that happens is a user request on the website. So the user connects to our website and requests a map, either by an address, entering an address, or an intersection that they want the map to be centered on. The engine, the TMAP engine, then takes the map data that it's got on the server and the location being requested and processes that along with a bunch of user-specific parameters, like, for example, what kind of Braille embosser do they have, what size paper are they going to use, do they use, what type of Braille do they like to read, and what scale is the map going to be, a bunch of other parameters, and churns out a tactile map file. So that file can either be downloaded or sent to a professional service for embossing, so that it would then be snail mailed to the user. And finally, either by embossing or by snail mail, the user finally gets the map into his or her hands and is able to get information about the street network that was never before available. So the technology that we're using underneath is the map data is from the Census Bureau. It's the Tiger line data, from which most commercial GIS data sets are built. But it's, some people sneer at it, some people don't sneer at it, but the fact is that it's free. So, hey, it comes at a good price. We use MATLAB, compiled MATLAB, to do the geocoding and the map production. That's because it's easy to rapid prototype in MATLAB. They've got a good maps toolbox that can be used, but ultimately this is something we want to move away from, doing things in C++ or Python or something like that. The user interface is programmed in PHP and HTML, and that's what does a lot of the website and also the telephone interface that we're working on using voice XML and PHP. For keeping track of user preferences and map history, we're using MySQL to be able to provide the user with, so the user can specify their preferences once and be able to recall them back and stuff like that. So we also support a bunch of different file formats because the idea is to provide printer-ready files. And so there's a standard set there's a specific file type for most older Braille embossers, which is called BRG. That supports a bunch of different embossers. Then there's some other ones. There's PRN, which supports some of the more modern, high-resolution Tiger printers. The code word Tiger is used too much. So anyway, there are printers called Tigers that have nothing to do with the data set and nothing to do with the Apple screen reader. And then we also are now more and more producing SVG, scalable vector graphics, which has some advantages that I'll talk about. I want to mention a little bit about tactile hard copy and Braille embossing. One of the neat things about Braille embossers is that they, by and large, are workhorses. The way they mechanically work is like a heavy-duty dot matrix printer, but instead of inking dots on a page, they poke holes in it, and the holes on the reverse side turn out to be dots. So it's the same technology for embossing Braille as it is for doing tactile graphics, The beauty of a Braille embosser versus a dot matrix printer is that, or some other kind of printer, is that there's no toner. So even 20 years later, if you've kept the thing in decent working order, it still works. And this leads to a lot of different embossers. You know, there's a huge embosser fleet out there that aren't necessarily modern, but they still work. And so there's only an increasing number of embossers available to the blind and visually impaired community. They tend to, more and more individuals have them, but in fact, institutions like libraries and schools and service organizations for blind folks tend to have Braille embossers. And it's for those, of course, who don't have Braille embossers, as I mentioned earlier, we would like to ultimately partner with professional Braille production facilities to be able to professionally produce these tactile maps and snail mail them to the user. This is what I'm now showing a visual version of a TMAP. I'm also going to, I think, let me just hand out some of these tactile maps that I brought with me to my enormous audience here. Is there somebody that wouldn't mind handing these out? Okay. So there's a couple different maps here, and they're labeled. The stapled ones have Braille keys associated with them. The sighted people don't need the Braille, the stapled ones. And there are two different versions of this map that I'm handing out. One version is a map that I made of this area, the Googleplex. But of course, it doesn't show any of the streets internal to the campus. It just shows where the outside streets are. And this is a suburban area where the streets are fairly wide apart. I used a scale of 1 inch equals 500 feet, which is a little bit loose for an environment like this. And one of the things that we're working on is an automatic scaling algorithm that will provide users automatically with an appropriate scale for the geography. The other map that I'm handing out is a map of your New York City office on 9th Street, or 9th Avenue. And that is a much tighter grid in Midtown Manhattan that provides you with the same scale, 1 inch equals 500 feet, but a better view of how a pedestrian, because I don't think that a pedestrian would use the map that I made here of the Googleplex other than to just say, ooh, I ain't walking anywhere, you know, I'll stay here and have lunch in the cafeteria. But in New York City, you can see that that street network is much more complicated and interesting, and would be much more usable and helpful for a visually impaired pedestrian. I'm going to point out a couple of features of these maps. They're standard on all of the maps that we produce. At the upper right-hand corner, you'll see a little Braille Braille text, if you will, and underneath that, a short line that's about 1 inch long. That's the scale. So above that line, it says 500 feet. Or if it were at a different scale, it would say a different thing. Or if it were in metric, it would say, you know, whatever. At the center of both of these maps is a small circle, a loop, that shows where the address is that was requested. And it shows which side of the street it's on and approximately where on the block it might be. That's done with interpolation of the address range. So also at the top of the map is a Braille legend that says the requested location. So 1600, I gave away all my maps, 1600 Amphitheater Drive or Parkway or something. And then the other one is, anyway, the location in New York. So, yep. Great. So, so basically, these features are standard on every tactile map that's produced. Sorry, it's 76 9th Avenue in New York City. So one of the big problems for Braille tactile users of tactile maps is that since making maps by hand, tactile maps by hand, is more of an art than a science, every cartographer would use a different scheme, a different set of labeling methods, different shapes, different, anyway, you get the idea. And so each blind user, when introduced to a new tactile map made by a different cartographer, would need to first understand what the map format is and what the information means. So there's this learning curve that's introduced at the beginning of every handmade tactile map that really slows down the process and makes you say, forget it, just tell me where I'm trying to go. Whereas with TMAP, since the maps are standard, the first time you learn the features and the organization of the map, then every other map is then that much easier for you to understand. So that's a really key feature, is standardization of these maps. Another thing that I just want to point out is that all of the Braille labels are oriented at the ends of the streets around the edges of the map, around the perimeter. There are no Braille labels interior to the map itself. That's for a couple of different reasons. One is that in a tactile map, your enemy is clutter. The more clutter there is, the harder it is to read the map, and the less useful the map actually is. So text labels interior to a map, I believe, lead to a lot of clutter and confusion, because then you need to worry about which feature is this label referring to, and is it covering up other features of interest. That's eliminated by putting the labels at the edge of the map. Of course, there are some streets that don't hit the edge of the map, so they don't get a label. This is also a motivation to use audio tactile maps, because on an audio tactile map, every feature gets labeled, whether it's interior or exterior. Another reason to leave the Braille only exterior to the map is that many Braille embossers can do Braille dots of only one height. The embosser that I used here actually can do multiple dot heights, so it's easy to distinguish the graphical features from the text features on this map, but that's only because the graphics dots are lower in elevation from the page than the Braille dots. On a Braille embosser that doesn't have that feature, you need to keep your Braille well separated from your tactile graphics features in order to make sure that your user knows that these are text objects, not graphics objects. Another thing about the maps, by the way, is that north is always at the top. This leads to street grids that are often at some angle to the page itself. But the feedback we've gotten indicates that actually that's more useful than problematic, because it actually gives you an idea of where true north really is, which is something, ordinal directions are something that blind and visually impaired people use a good deal more than most sighted people, because they do a lot more talking about which way they're going to people who might be giving them directions. Before I move on, any questions about the map organization? Okay. So the audio tactile maps that we've been working on use SVG as their file format, and that's really a great thing, because basically what it allows us to do is embed in the scalable vector graphics all sorts of labeling and annotation information. So each street segment, in addition to being grouped with all of its other street segments, has a text label, so it's got a name, and then it's also got embedded into the description field a number of different pieces of information, including what the address ranges are, on which sides of the street, how many lanes of traffic there are, whether there's a median or not, and ultimately we can embed all sorts of other information, like which side of the street might be better for a blind pedestrian to walk on than another, or whether where crosswalks are, other other sorts of information there. So that's easily embedded into SVG. And in addition, we can transmit a single file to the user. The audio-tactile software that the user has on their machine, which I'll talk a little bit more about in a minute, it will be in charge of taking the SVG and rendering it into a tactile version using a Braille embosser, and then also using that same file to do the corresponding digital information for what the user might hear when touching specific features. And you can also link SVG to audio files and stuff like that. So that's a great, it's a great format for us. And Raman and I have talked a little bit about KML and other formats that really have potential for this as well. But SVG is what we've been using at this point. So this is an example. This is an image of one of the audio-tactile systems that we've been working with the most. It's called the Talking Tactile Tablet, or the TTT, from a group called Touch Graphics, Inc. They, until now, have been producing very nice maps of the world and other educational materials based on audio-tactile technology. But now we're partnering with them to produce talking TMAPs. And they'll simply download an SVG file, as I said, and print it out using their software. And then the user can touch the map anywhere and hear what they're touching. There are some technical aspects to this that I don't want to gloss over. One is that when you put let's say you've downloaded 17 different tactile maps and printed them out, and now you've got 17 pieces of paper, and you want to put map number 3 back on the tactile tablet. How does the computer know which map you've got on there? So what they've done is to put essentially a barcode at the top of the page, where you touch 3 spots along a bar that has 20 possibilities. It's a fairly big namespace, and the computer then can identify, based on the locations of the 3 spots on the barcode, which map you're going to be working with, and can automatically load the digital file associated with that. Also, on each of the TTT overlays are some UI features. One, for example, is this cursor cross and a select button in the middle. All the UI features are off to the right hand. Off to the right from the map workspace. So the cursor cross can be used for things like scrolling through a list of streets that are on the map, or possibly scrolling through an alphabetical or geographical list of other features that might be included on the map. And then when you find the one you want, you can select it. So that can be used for, then it can guide your finger, for example, to that location by telling you left, up, down, right, and then it tells you when you got to the location. The numerical keypad is just a tactile drawing of a numerical keypad, and that can also be used for entering data or making menu selections. You, for example, could enter an address using this keypad, and then your finger could be guided to a specific address in the same way. And then there's an escape key at the top, which you use for saying, okay, I'm done here, I'm going to load a different map, or work with a different type of tactile overlay. So a couple of other features available in this prototype of the talking TMAP is you can do multiple taps to get through information. So for example, the first tap tells you the street name. The second tap might tell you, might spell the street name. The third tap might tell you what the address range is on that block. And you can keep tapping until you cycle through all of the information. So that's a very nice way of layering information on a map without a lot of complex user interface elements or going through menus or whatever. You can also do distance calculations. You touch along a number, you touch waypoints along a route and it adds up the route segments. As I pointed out earlier, you can use the cursors to scroll through a list of features and have your finger guided to a position. And that can be done for streets or points of interest. You can also have your finger guided to an intersection just by selecting street 1 from a list and then street 2 from a list of streets that intersect with that first street. So that's, we're hoping to do a lot more with that. So if there's any stuff that I haven't covered here or stuff that you want to know more about, you can go to my the website, which is www.ski.org/TMAP, or of course you can email me at tmap@ski.org, and I'll elaborate on all of the things that I glossed over today. I have a bunch of collaborators at Smith-Kettlewell and Touch Graphics: John Braben, Debbie Gilden, Steve Landau, Bill Gary, and Tom Fowle, and many others. Our work has also been funded through the Department of Education, the National Institute on Disability and Rehabilitation Research. And we're certainly hoping to do a lot more with this. This is at a very early stage, so we're hoping that this talk today can produce some ideas on your side and ideas on my side maybe, and we'll move forward in some fashion, hopefully to make this a real product that can be used by blind people who really need it, rather than just a cool demonstration that I'm doing as a research project. So I just want to say thank you, and of course, if you want to get in touch with me, there's my email address, and that's it. Any questions? Yes? No questions. I was totally clear?
So one clarification on KML. I didn't mean it as a replacement for SVG for you as an output format. It's actually, it would make an input format for your Tactile.
So
what KML actually represents is at a very high level, because you use street information with heading and direction and all that stuff. And so the Tactile maps that you're producing draw the thing, you could actually drive that from there. And then from it, produce your SVG.
So you're clarifying what I maybe misunderstood, that KML is actually could be a source of data for me,
yes.
And that can be then re-rendered into whatever other format might be appropriate for my users. Thank you. Any other questions? If not, class is dismissed.
Thank you.
Thank you.